the reservoir is temperature T. The gas is moving so fast, close to the speed of light, it will boil down, it will melt itself, because the theory, even the theory may break down. So, but in non-relativity limit, you don't see this. And okay, let me, of course, the zero temperature goes to zero temperature because it's a ratio. If T is 0, it goes to 0. So it will not change the third law. Okay. Maybe I start with superfluid, then there is a critical velocity. So that's why the velocity cannot be too high. As Zhong Yuan asked, there is a critical velocity. If your boost velocity is too high, it's not superfluid anymore. So that's why this formula is very difficult to test. Now I stop here. Here I would say I derived the case A. There are several other cases. Okay, for case A, internal energy is the same as external energy. But in other case, they may start to split. So I stop here. We have 5 minutes break. I will, rest of the lecture, I will give you physical interpretation of this. You got this answer, you may not be very comfortable. But let me give you some physical explanation. Okay, see you in 5 minutes.
老师，你如果把时间孵化了，你再做洛伦兹变化，你的空间自动就有缩。
对，空间自然就有个 I， 但是呢，这个空间呢，我还是实的 ，Ix 就是虚的。
对，那这个意味着什么？
这个意味着就是说，空间的这个虚部只要不局限在任何物理量，我没有把空间把它变成复数，我空间乘以 I， 我空间还是实数，我这个时间不一样了，我时间把它复数化以后，它就真是一个复数了，它有实部有虚部，你空间做罗伦兹变换。 我是11点，我是10点50就在一起。你这个，比如说一个人，他这个他嘴里说的跟他肚子里的想的还是有时候是不一样的，就是这个意思，是吧？这个你想的你都说出来是不太可能，你说出来的有时候跟类人有时候一致，大部分情况都一致，也有不一致的时候。我想就是这个意思。我想 ，so internal energy determined by the relative motion between sample and the reservoir, independent of the observer. The energy, the temperature was determined. The observer, no matter what you do, they get the same temperature. That's something I want to stress. Okay. However, the thermodynamics also involve the volume. Then it's extensive quantity. Extensive quantity. There's also Doppler shift energy. Then we have to say what's the observer. When I derive this temperature, I use this co-moving star frame. That means the observer and the reservoir are the same. They're not moving. But the observer can say, why should I be static? I can also start to move. The observer can move. Okay, in this case, well, the role of the observer, I can say, so for case A, is V1 equal to V2 equal to 0. So in this case, internal energy equal to Doppler shift energy. And for case B, sample is not moving. Only the observer is moving. In this case, the temperature is not changing. But the volume, observer is moving, they still see the volume. The volume of the sample still change. Because it's Einstein's special theory of relativity. Okay. In this case, the internal energy is the same as the static case. Why? Because the sample and the sample and the reservoir are not moving, so they determine internal energy. However, 如果有个内人，当然有个外人了。但是大家为什么不提呢？ Because both are moving. In this case, then you will see the temperature has gamma 1. Volume is the relative velocity. Because this is the structure, this is semiconductor. Okay. In this case, gamma 1 not equal to gamma 1, 2. Internal energy not equal to Doppler shift energy. So 里外不一了，这个情况里外不一。我想打个比方，比如说你跑步，你不跑的时候就很平静，你跑起来以后，可能你说话就有点费力了，就这个意思。Okay, co-moving case. Let me say, people they ask this question. Okay, in a superfluid case, for example, superfluid case, I want to stress this part. This part people had a dispute with me. For superfluid, okay, for superfluid, it's moving. I measure this temperature. The static observer measures this temperature. People always ask, okay, suppose I do an experiment. The observer is moving together with the reservoir. It's called co-moving. What temperature did it get? It still gets this temperature. Why? Because the internal energy is determined by the reservoir and the superfluid. Has nothing to do with observer. Observer not moving or moving together with the sample, you get the same temperature. Because it's independent of the observer. Physically is 类人不依赖于你这个 observer, independent of observer. Observer keep running, so what? You just change your own speed. Does not affect 我们的类人。类人是跟 reservoir 决定了的。That's why the temperature will not change. So in this case, co-moving case, the temperature is still the same. It's gamma 1 determined by velocity of the relative to the reservoir. But the volume, co-moving frame, they're moving together with the superfluid. They don't see total energy anymore because they're moving together. The volume, the system volume is the same. Okay, in this case, so that's why the co-moving frame is different than the co-moving star frame. Okay, so so co-moving frame, you see the same temperature as before. So this Doppler shifted, but they don't see Doppler shifted energy anymore because, but the internal energy is still there because the reservoir and the sample is still relative motion. So this I want to stress is when the sample and the reservoir there's relative motion, the temperature is fixed. Maybe one boy is on another girl study, they get the same temperature because 类人。我们的内部的事情你别来管我，就是这个，不要干涉我的内政，就是这个 reservoir 跟 sample 是内政啊。你 observer 你爱怎么动怎么动，我们的温度就是这样，你爱看不看就这个 temperature， 你怎么动都是这个 temperature。That's why I want to stress this. In the superfluid system, I know is completely right because I did the microscopic calculation when C goes to infinity. Okay, I also challenged the experiment. This explains a lot of this distinguish between 内人和外人explain a lot of exotic phenomena. Okay, so in general case, I would say the temperature, actually this is very intuitive because volume and the temperature. Temperature can be considered as a finite size in the imaginary time direction. Okay, the volume is the finite size in space dimension. Temperature is the finite size in the imaginary time dimension. So they transfer slightly different. One is internal energy, another is combined with Doppler shift energy. Okay, so I want to explain this process a little bit physically. Why the temperature changes from a physical picture. For example, when a sample and the reservoir reach equilibrium, the temperature is T. Okay, now it starts to move. I have to do something, right, to make it move. Because the sample and the heat reservoir exchange heat. So you have to do some work. How it speed up to a finite velocity? I push it, then you do work. The work goes to the sample, and some heat goes to the reservoir. Okay, so energy conservation, the two heat plus some kinetic energy. Of course, second law is always entropy increase. So this process, when it reach the equilibrium, there's no more heat. So there's no more heat. I want to say is for canonic ensemble, then when they reach the equilibrium, there's no more heat go to the sample because it's reached equilibrium. But there's still some, because there's still some exchange between the heat reservoir. Therefore, the reach equilibrium, there's still heat go to the heat reservoir, but the reservoir temperature will not change. Why? Because you provide some heat to the reservoir temperature will not change because reservoir is a big guy. You give some heat, specific heat is infinite. The temperature will never change in this case because 你到雁西湖去，你倒一杯水和拉一杯水进来，它的这个水面不会变，它太大了。你这一点算什么呢 ？Here is the same. The reservoir temperature will not change, but the sample has finite specificity. The temperature will increase. However, the temperature increase, you have to be very careful because the temperature increase is the intrinsic part. There's also heat part. Okay, so when they reach equilibrium, there's only heat. There's no more heat go to the system. We go to the heat reservoir. But there's the two parts because there's a collision, the temperature change, but there's also due to the collision, the friction part. Then my claim is, if 我就过河车桥，我把这个 Epsilon goes to zero, reduce this part. Then my bet is the intrinsic part will have a slightly higher temperature than the heat reservoir. That's my claim. At the end of the day, 我达到平衡以后 I remove the contact with the reservoir, get rid of the friction part, you will get the intrinsic part. Let me explain this. You hopefully clear in your confusion. Maybe you keep your question, okay? Now from this Lorentz algebra, we know. I want to explain the physics is Lorentz algebra, then C goes to infinity, goes to Galileo algebra. Okay, so I want to explain the physics is momentum, also center of mass momentum. So why the temperature change a little bit? This you can actually it's not center of mass anymore. It's called the center of momentum. Classically, center of momentum, then there's no way to decouple. There's no such center of mass theory anymore. If you learn mechanics, only in Newtonian mechanics, center of mass decouple with center of mass decouple with the I can get the center of mass, and then I do whatever center of mass, and then I do whatever do center of mass, because center of mass, even in center of mass is not a mass, even in center of mass is not an initial frame. It always decomposes into two motion. But for relativistic effect, compose into two motion. But for relativistic effect, no, because relativity you get this square root. There's no way to decouple. Relativity you get this square root. There's no way to decouple center of momentum from is internal motion. So in this case, I want to say is because I push this sample. Relativity this also affect the internal motion. Therefore, the temperature will be slightly higher, and then the yeah.
Is there a heat transfer from powder to?
Yeah.
Is there a heat transfer from powder to?
Exactly. Exactly. That's what I said. If that's what I said. If we are not relative motion, we have the same temperature. If I higher than you motion, we have the same temperature. If I higher than you, there's a heat transfer. If there's no relative motion, but if you transfer, if there's no relative motion, but if you stay there, I start to running, then my temperature should be slightly higher to reach equilibrium because I do two jobs. You only talk to me because I do two jobs. You only talk to me. You are not moving. 你以逸待劳 but I have to moving. 你以逸待劳 but I have to moving. Then my temperature should do two jobs. One is keep me moving. Another is talk to you. So, but these two motions are not decoupled. Only in C into infinity, they're completely decoupled. There is no to reach equilibrium similarity, but different. In the relative side, it's called. There is no to reach equilibrium similarity, but different. In the relative side, it's called the Tolman effect, due to the gravity. Yeah, I will make a comparison at the end of the slide. They are related, but different. This is Tollman effect. That's what they mentioned. But different. This is Tollman effect. That's what they mentioned. The Tollman effect. Yeah. Okay. Now at the end of the day, I will say, what's the experiment? You make this prediction. Experiment. You make this prediction. The experiment, what did we say? So unfortunately, oh, there's one thing. How much time I have? Okay. How much time I have? Okay. 20 minutes. It's okay. So how to test this? At the end of the day, there's one analogy I forgot to. I push this sample, then the temperature definitely increase. 那么你剩下来的这个温度，我把它叫intrinsic velocity.
There's no heat transfer. Keep push the sample. The work on it that it keep transfer heat to the heat reservoir.
Oh no! Here is in order to keep the sample moving, I only need to apply infinite force to count the friction. This heat will go connection with the reservoir. It looks like an isolated system. Then I conclude, get back to Einstein's original problem. If I push a microcosmic ensemble, okay, microcosmic, no reservoir, then because relativity effect, I push a box of gas, a particle, the kinetic energy increase, but because the motion, there's no decoupling between center of momentum and the internal motion, so the temperature still increase. For non-relative case, you push a box, the temperature, because they decouple, you just change the velocity without touching the internal motion. But here I conclude, even for microcosmic ensemble, the temperature still increase, even for microcosmic ensemble. So if I use these, but how to test this experimentally? Unfortunately, this effect is very small. For if I use condensed matter system with chromatic ensemble, the velocity is very small. In the superfluid helium, the velocity is only 60 kilometers per second. If you after that, it's not superfluid anymore. Because why I want the superfluid? Because superfluid, even this part does not exist. Because superfluid is flow without resistance. There's no friction. So there's always no this part, only this intrinsic part. So use superfluid. This experiment is very easy to perform, but this effect is very small. And then, yeah, I want to say one more thing. Talk about the temperature and the volume, as I said. What about the other physical quantity? Many people will say, okay, there are many papers. But why I don't like these papers? There are probably thousands of papers on combined spatial relativity with into thermodynamics. Very complicated papers. But why I like my opposite? First of all, my point is clear: statistical mechanics. Then temperature and the time are combined into complex. That's it. Very, very clean. I don't play with this thermodynamic relation. Then the two general transformation is universal. One is volume, one other is temperature. I draw this. I used that picture. The volume, how volume transform. The temperature, how it transform. Because both are finite size. One is finite size in space. Another is finite size in imaginary time. So they transform, get the same fact, but in case say the same fact. So this is very intuitive, okay? Also looks very correct. I don't play with thermodynamic relations. Extremely complicated. The many papers extremely complicated. You don't know. I don't think they remember what they did. Here I remember because it's a very clean calculation, statistical mechanics, and also plus complex time, and but not a complex space. Okay, so at the end of the day, if you look at the free energy, for this experiment, I thought in particle physics how to test this velocity, this temperature effect. Particle physics, because the big equipment cannot move. Then there's the cloud. If you make the cloud move, but how you do that? If you make the cloud move with high velocity, then it may the temperature will increase further. That's my prediction. But how you make that colliding cloud move, I find it very difficult. Do they do this experiment? They usually do this center of momentum zero region, the cloud expand. If you make it move, the temperature will also increase. But I don't think that experiment can be done. So we have to resort to condensed matter. And the particle are not, I got the emergent particle on top of it, okay? So I got free energy, KBT, volume, and density of states. I can also get the number of particles. Of course, it's not conserved. It's like a photon. The number of particles is not conserved. Then the density of states. For the so I can do this transformation. Then I can see this fact is Bohr distribution. You can see this gamma get cancelled. So here, this factor actually you don't see relativity effect. The temperature and then Doppler transformation get cancelled. So it's very similar to non-relativity because it get cancelled. It's the same thing when you're not going to see this effect. You get cancelled. However, the density of states, you can still see these major changes. So you can see when the momentum transform, there's a Jacobian, because you have to perform the law. You have even it get cancelled in that Bose-Einstein distribution. So it still depends on this velocity. That's what I mean. So this spectrum can be mapped by Mu-Chun scattering. And unfortunately, this fact is very small. You look at V over C squared is 10 to the power 15. So is this measurable or not? This is kind of temperature effect, okay? So actually, you compare with gravitational wave, is 10 to the minus 20. This is gravitational wave is 10 to the minus 21. The frequency due to gravitational wave shift. So that has been measured. So here is 6th order of magnitude bigger. So I don't know how to measure, but definitely atomic clock twin years group is close to gravitational wave. Gravitational wave, the tiny effect has been measured. So this temperature effect can be measured, definitely. What I like to say is, even it gets cancelled in this Bose-Einstein distribution, it appears in the density of states. So I like to say is the temperature and the volume transformation is very universal. But the free energy has to depend on what kind of excitation you are having. Okay. Depends on the specific. That's why I addressed all these problems. I avoided. I started from statistical mechanics. Started from the time has to be complex, include both real time and the temperature. Both are important. Okay. because when the system is moving, real time is important. Temperature is also important. So maybe I have 10 more minutes. Okay, so I want to say, summarize, because this is special theory relativity. Okay, length, time, and mass, and also Doppler shift. Then the temperature is a new unit. Okay, temperature is Kelvin, is a new unit, and in this case, it's for equilibrium system, the status is the same as the temperature for equilibrium system. Therefore, the temperature for case B is not the same. So for case A, there's an increase. That student they mentioned the Tolman effect. In the gravity side, there's a horizon radius. It's very similar formula, but the physics are different. So this is called the Tolman effect. I don't have time to explain. It's all T over tau, coordinate time over there. But this derivation is really tricky. Okay, as I said, it involves a lot of physics. But at the end of the day, it's similar to this Tolman effect. So why, as I said, let me get back to Planck, Einstein. I think their angle has a lot of limitation due to the time, because they start from thermodynamics, not statistical mechanics. So that's the difference. Also, statistical mechanics automatically unify temperature and the time. And so in case A, I got temperature increase, internal energy equal to Doppler shift energy. But for case B, they didn't distinguish these cases. Okay. So this thermodynamics is very complicated, easy to make mistake. So I take a different route. I think I resolved this problem is when case A, the temperature increase. Case B, they didn't distinguish these cases. Okay, because they did not start from the statistical point of view. Of course, there could be a black hole side story. That is more, or maybe we can chat some next time. Before I conclude, I want to explain one small thing. I have a few more minutes here because a student asked me, I skipped that slide about, I'm talking about the equilibrium system. A student say, what about the non-equilibrium system? Non-equilibrium system, actually, I want to make one slide to explain maybe it's also related to statistical mechanics. What do we mean by statistical mechanics? How we distinguish equilibrium system with yeah. So maybe so I will talk about the equilibrium system, which has a well-defined temperature. But one student asked me, what about for open system? They interact with a reservoir environment. You see, for equilibrium system, there is an interaction, but the difference goes to zero. At the end of the day, after reach equilibrium, there's the epsilon effect. Even Carter didn't discuss it carefully. So when epsilon goes to 过河拆桥以后 then actually the equilibrium system with a finite temperature T. But the open system is a strong interaction. Epsilon goes to 1, it's non-equilibrium system. So this is look at looks like quantum optics. Okay. So for equilibrium system, the density matrix satisfies Heisenberg equation of motion. And you can, when you reach equilibrium, you can derive canonical ensemble. For non-equilibrium system, for non-equilibrium system, you get this density matrix is a master equation, okay? Because there is a bus, there is a dissipation described by gamma, and if you drop the jump, then you get this so-called non-Hermitian. So in this case, equilibrium system has well-defined temperature. That's what I'm discussing. For non-equilibrium system, the temperature is not defined. Then you don't need this temperature concept, just real time. Okay, that's the main difference. And then I would say this corresponds to the ADS geometry. This corresponds to the DS geometry, because DS geometry is this is open universe. That's definitely a non-equilibrium system. And I focused on this equilibrium system, which has temperature, both temperature and real time. In non-equilibrium system, you can just forget about the temperature. Okay, thank you very much.
Thanks, Professor Ye, for the very interesting talk. Any more questions?
Yeah, Zhongyuan has a question. I don't know my answer it or not. I saw the student had a lot of questions in there. Can you continue to ask? Yeah.
So you say you mean if there is an observer is moving, so he will observe this original system will be a different temperature, right?
No, what I mean is when observer is moving, as long as the reservoir and the sample is their relative motion fixed. Yeah. No matter observer what moving, how he moves, will not affect the temperature, because the temperature is determined by the internal motion between the reservoir and the sample. So the observer can move together with the sample or not moving or whatever. The temperature will not change. What will change is the volume and the Doppler shift energy. For example, I measure the Doppler shift energy, that's external energy. It will not appear in the free energy. In the free energy part, all these are internal energy. That's why in this free energy part, I want to say if you calculate the system's free energy, this is the important question. Okay, for example, if I calculate the system's internal energy, if the sample is not moving, you just perform all this calculation, specific heat, whatever. However, when sample is moving, so for example, the superfluid is moving, what's this energy? This energy is the internal energy. We're not, suppose case B, the observer is moving. It will look at what will the measure. They will measure Doppler shift energy. But that Doppler shift energy, you cannot plug it here. Plug it here is internal energy, because the reservoir and the sample is not moving, so they will not move. But the only change is the volume. So what plugged in free energy, all these guys are internal energy. That's what I want to stress. If you look at the case B, the sample and the observer are not moving. The sample and reservoir, but the observer is moving. Observer will measure Doppler shift, of course, because he's moving. But that Doppler shift energy you cannot plug in here.
Okay.
What plugged in here is determined by the reservoir, is internal energy. So that means 里外不一。我这个跑动的人看到的是外人，但是外人你不能放在free energy 里面，free energy 是内人。
Okay, thank you.
我的 physical interpretation is when you are running, you change the kinetic energy of your own. Right? Why should I? But the internal energy of the sample will not care about you.
Yeah.
Because you do whatever you want, you run 1 meter per second or whatever. You measure the Doppler shift. And also Zhongyuan asked the Doppler shift could change the sign. Okay? Now I want to stress this. This is important because I chatted with this experimentalist. I got a lot of, response from him. If you measure Doppler shift energy, actually system has this slope. If you run fast enough, for example, this velocity is 60 meters per second. Suppose you riding a very fast stuff past 60 meters per second. What will you see? You will see Doppler shift energy becomes negative. But the system does not care because the internal energy is not moving. It's not. This is case A. Okay, I'm talking about the case B. This is explained. If you run fast enough, the Doppler shift energy will change sign. That's what you see by you, but the system will not have phase transition because that's you. What you see is a superficial case. However, if the sample is moving, when sufficiently fast, indeed it goes to a different phase. So that's explained a lot of phenomenon which you cannot explain by special theory relativity. From special theory relativity, naively, whoever moves should see the same thing. But here it's very different. Sample moving, you see phase transition. Observer moving, you see nothing. But you see something. You see Doppler shift. But what you saw is 外人，就相当于我心里想这么想，我怎么说，反正我怎么说都行，反正不影响我的内心，就是这个意思。This is a good analogy. Yeah, good question. Yeah.
Okay. Could I also have another question?
Yeah.
So could you turn the slides to the discussion about the particle physics? That diagram.
Particle physics. Yeah. I would like to say a few words about particle. I forgot. Yeah, particle physics. That diagram is, first of all, I want to criticize these people keep saying grand canonical ensemble. This is not grand canonical ensemble. But why they want to use chemical potential? They just a mathematical trick. There's no reservoir. Okay, there's no reservoir to exchange particle with the system.
Okay.
But I mean, if I could do an experiment, make the cloud moving, then it will also have this effect. But how? I don't know how. Experiment particle physics is very hard to manipulate things. How you make this colliding clouds moving? What's your question?
Okay, my question is, so you see, when we describe the star system, we should use a micro-canonical ensemble. But I think this is not true because in the cosmology, we know the universe is expanding.
Yeah.
So the energy is not conserved.
Right.
So we can only define the temperature, but so what I mean is that in cosmology we should use temperature but not the energy. So maybe we could use somehow canonical ensemble but not the micro canonical.
You are right. You are perfectly right. That's I answered this. I think I said this. You expanding universe, you have to be very careful. It's a non-equilibrium system. Okay, it's not no energy, no temperature. Okay, that's what I mean. In expanding universe, you don't know what it is. Energy is not conserved, temperature is not well defined. But I would say this: expanding universe is more like this open system. Okay. I just explained this slide. Give me one more second. Okay. It's more like DS geometry, or in this case, energy is not conserved. With Jun, we charted this DS geometry. There's a called cosmological horizon. Outside the cosmological horizon, what it is, we don't know. And the expanding universe, the metric is time dependent. That's really not the case here because energy is not conserved. The temperature, people use microwave background, 3.7 K. You know, that's an approximation. If the expansion at the given short period of time is quite equilibrium. If the expanding is, if we look at the time scale, much smaller than the universal time, approximately we treated it with some temperature. Yeah. But if you look at the global picture, it's really not the thing I'm talking about because we don't know. It's an open system. There could be something big outside. The temperature, both temperature and the energy is not well defined.
Okay,
Very nice question.
Okay, due to the time limit, for more questions, please ask Professor Ye in private.
Thank you.
So let's thank him for two very inspiring talk.
哎，我把这个给抽了啊，直接抽了啊。好。
您在这儿，您这所有的温度的定义应该都是
我先拿下来
啊。
应该都是相对能量的偏或者微分的那个，那个从那个定义导出来的那个。
那个你讲的是这个我还没有文件，真正的推导，
不需要考出来，就直接放，
我觉得
都可以。这种没问题。
我现在是倒过来，就假定这个，我就对撞的，
就是考到这个电脑考不考都。
华电学帮你就是
好像可能
是不是我没有这个推导比较，我一直没有推导。我现在这个推导就是应该把这个推进去看头啊，真正的推导我没有推，就是看推进去看头，把这个时间到复数法，
考到这个
然后
考到这儿，
实不是温度，是周期虚不就是实时，然后我要做个变换，但是没有，但是我想这个结果是对的。Very nice。
您不说这个温度它和速度相关，但是安鲁效应不是说温度它和加速度相关。
你这个问题我问的你应该在那个时候问。安鲁是这样看，安鲁效应是这个observer加速运动我这是匀速，你这个加速observer加速运动，看到那个它有一个温度的。有一个温度，这是我的吧？
这都是您的。
我的喝完了。对，我应该提一下安鲁效应，没有时间。安鲁效应不一样，它是有加速运动然后呢，零温变有限。我这是有限温变有限温，它是一个 ratio。我这是，而且那个安鲁效应是不一样的。安鲁效应它是一个零温的东西变成有限温。跟加速度成正比。
但是这我觉得很奇怪，就是温度它到底是和观测者的什么运动方面？因为你这个如果是和速度的话，也就是惯性到另一个方面。对。但是如果是加速的话，就是从一个到那个非惯性。所以它温度呢，它这个温度是加速的，
安鲁效应安鲁效应它是因为安鲁效应它是因为安鲁的。安鲁效应有加速度，我这个是安鲁效应第一是不矛盾。比如说因为我是这个我是 t 等于0还是 t 边它那个是我这是 t prime over t 如果温度是0 t prime 也是这个跟安鲁效应就是说跟你的考虑就是考虑周特性这些温度包括刚刚那个说的全部是对，实际上能做不到我们是所以包括这个安鲁效应但是我们确实有好多问题如果这样说这个对那我们说安鲁效应这个就是有它每是每个速度大小不一样也就是说它应该一直在变所以说这个时候我们看所以这个加速度是常数的话它是怎么的这个安鲁效应我今天不敢提它是如果这是一个中空是0 个 Q state， 然后我加速运动以后呢，我就看到一个叫 InternationalAcademy，InternationalAcademy 呢，我就推出了在这外面我看不到，了，我就把它 trace 掉，就是一个 Q state 到 mix state，mix state 就有个温度，这个温度就证明它的加速。这个物理跟我这个完全不一样，因为我这个 case B 还有点像 case B 我民宿运动我温度不变，case B 的温度是不变的。阿姆效应是在 case B 的情况下找到加速度。我的 case B 就是一个民宿运动温度是不变的，就是 regular。阿姆效应也可以。
你们这那个上课的要求吗？上课。
阿姆效应它是常用的，是一个分通。它有的是加速的执行。看到那个我其实不讲一方面方去那个就是这个跟阿姆效应这个是独立的，这样去case B。case B 你看，我民宿运动我温度不变。case B 啊，我认为它
折算出来。
这个物理不一样，阿姆效应现在可以，我这里都是外面的，可能就是
但是我主要想知道温度到底是温度应该算什么样，因为它是我感觉不缺老师，
温度啊，
也这个那个研究所的老师都可以来我们班，就是我们，当然我们比如说我们思圈要参与的话，我们肯定要教学，但是我们得自己去争取，不会有人给我们
温度显
看那个课，就是我们必须要自己去争取一个课然后来上，
这么多，就是想一想这个时间，
没有，
就是时间变成 flat 了，还有这个空间配备，但是空间没有变。
对，
但是我其实
很难跟谁调整这个你就刚好就是有这个，因为看得上去是实验方面但是你把时间方面化之后，
反正用中文讲就用讲都是一个
然后把某一个量，
很多老师把所有的一个
反正现在就是因为讲的话，这个时候的群当然应该没有太大的
这个群呢，
一个是回答，还有一个本来就有的这个我当然想问下我不是现在就是说，
但是他这块儿他也是我们由变化的，他也是特殊的，他和那个阿姆效应就跟我们这个研究所量也不一样，这个
跟阿姆效应完全不是阿姆效应，
对啊，我的意思，
阿姆效应
有点特殊，他就是
阿姆是说阿姆效应
也属于博的一个院系，但我们也是意大利的 ICTP 的分部。所以前几天实际上是有几个，为什么在这个时候办？就是因为我们有国际锅，就前几天有几个外国老师，但他们讲课就回去了。
首先我是民宿运动的话，温度不变。我现在就缺一个。
然后下午就您的报告之后还有一个，就是他会给一堂课，就是那种怎么说呢 ，public lecture。他现在是 IPMU 的主任，就日本东京大学，东京大学有个
这两个都很好学。然后我做变换，做变换的时候就看到温度这个变，物理学会有点温度给是温度上一个是一个某种情况下 A 对应的是不一样，
可能是，我觉得就是说，反正就是说，比如说高能理论，就是日本最有名的就是一个东大的 IPMU， 还有京都大学的哈瓦。
因为这两个计算就 A 和 B， 但是西语有限，没有一个没有一个单数正确问的，有刚刚说配码的是，但是这些结果啊，我去的时候是很马的，
有结果，加速运动就不是说你的这个是一系过来，我的应该是做高的，做高方，但是没有比较后之后，就是说按照下来，英文建筑有，估计对，估计是30分钟，对对，就是。按照下来，我反正我不反我一加速我变成1点，我一开始不是什么。我再做按照下来，一开始就是
反正基本上都是日本。
我再做，物理界的大佬。我猜了一下，对，先有个量的系统，系统有个问题，然后按照下面是系统为零，它就是一个真空，然后加速，就看那个你这个玩意我看的
这个是
就是得挂在这儿是挂一下的。行，我就挂上。我还是拉上来。
因为这个我们线上转播，它就是不会扩音，但是你必须这样讲，线上才能听见。
哦，行，好。是我带有茶，我是。
就是上下翻页，最上面那个就激光笔，它得再翻一页，就有时候黑的时候你再翻一页就行。
好。
哎，这个但是不知道为什么大家不做，这才是一个真正的，就是另外你问的问题本身也跟
Okay, let's continue. So, the third lecture of this morning session, we're very happy to have Professor Wenli Yang from Northwestern University. So Professor Yang is a great expert on integrable models, and he's going to give us 2 lectures. So, the first one this morning, the second one this afternoon. So the title of his lecture is Quantum Integrable Systems and Their Solutions. Let's welcome Professor Yang.
首先我开始我用中文来讲，lecture 的话我用英文来讲，就是首先我非常荣幸来参加这个，实际上是非常有历史的，因为现在你们这一代人的话，你们可能就是觉得什么东西也许这些都是很自然的。ICTP 这个机构实际上是对于我自己上学的是80年代86年进的大学，90年上的研究生。那么在90年代那个年代的时候，实际上互联网并没有在中国普及。我是95年去的 ICTP， 那么当时给我看到的是一个完全崭新的不一样的一个视野吧。在某种程度上，咱们国内当时还是非常的跟国外的差距还是非常大的，而且呢，年轻人的这种机会也是非常少的。那么当时开阔了我的眼界，那完全一个崭新的一个。后来回来，当然我们中国现在发展的非常的快，到现在为止，那么现在互联网所有的我们几乎所有国际上所有的信息都可以很快就能得到。那么很大程度上，作为我个人的这个成长的过程中，很受到了 ICTP 这样给我的这样的一个机会。当时是他们资助，我96年博士毕业，95年去的那个地方。那么这个在学术上提高了眼界，同时呢，各种技术上提高了眼界。那么比我再长一些的，现在在国外的，不管是在国外的，我不知道叶老师，知道不？早期咱们国内 ICTP 是第一个跳板，咱们国内很多人出国的话，一个是受到了李先生的一个 Caspia 的一个支持，咱们国内的特别是物理方面的人出国是通过这样的一个渠道，那个渠道应该是在我想一想，应该是在78年、79年到89之后结束了。另外一个就是很大的一个地方呢，大家都是通过 ICTP。那么物理的、数学的，实际上也有。我在国外也碰到很多 很多老师，很资深的老师，他们是通过，所以我个人也是受益。那么现在呢，在吴老师的争取下，咱们中国 ICTP 也有这样的一个机构。我想全世界是不是中国和巴西，
可能
非洲还有。那么这样的一个机构，当然现在对你们来说，出国各种情况都不存在任何的问题。那么实际上这个也看到了咱们中国的发展，也看到了，吴老师实际上是给咱们国内的年轻人提供了一个非常好的一个平台。好，那么这是我个人的感觉。那么年老师说这个事情了以后，我觉得我非常希望来参加这样的一个活动。好，那么再次感谢祝会给我这样的一个机会，我也能在这儿来呢跟大家分享一下我前面这些年的一些工作。好了，那 I try to speak in English, so I will give two lectures. Actually, this is most based on the work during the past 20 years, more than 20 years. So the quantum integral system and the solution. Actually, Professor Ye gave the very important example as SYK model. SYK model is the particular exact Sorbonne models below to the CFT, and the CFT is a big branch of the quantum integral system. So I try to to give the quantum integral system overall about the most important one is the conserved charge. So integral system means they have a lot of conserved charge. CFT, they have a lot of conserved charge. And for all the model here, I am mostly based on the spin chain. They have a lot of the conserved charge. And also we know from the physics, especially for the理论力学. Actually, we know that if the system have the symmetry, then they correspond to have the one conserved charge. If they have enough symmetry, that means if the conserved charge, that means commute conserved charge. That is for the classical mechanics, that they should in the Poisson bracket commute each other. And in the quantum system, actually commute each other. The conserved system, the quantum particle, that means can factorize. If the system is the spectral can factorize, that means the system is the integral system, which guarantee this happened. That is a conserved charge. If you have enough conserved charge train on the two body, very important one is two body scatter matrix. So the three body scatter matrix can decompose in two ways by the product of the two particle scatter matrix. And this actually gave the equal, because final physics results is equal each other, is only one. So that should equal each other. That is the Yang-Bass equation. So I will actually all my talk based on the integral system based on the Yang-Bass equation. So Yang-Bass, that means the Yang-Bass equation is very important to describe the quantum integral system. So actually, let's start. Quantum integral system, as I gave the overall picture, that is enough conserved charge, guaranteeing you can, for classical finite dimension systems, that you can use the action and the angular momentum. That system is factorized. You can solve it. And in a quantum system, I just gave some picture about new. Of course, the first example is the classical dynamic system. Newton dynamic series plus gravity, we can solve actually for the one particle in the center. So for the solar systems, our Earth around the sun. That means you can solve everything. We know that the angular moment, because this this potential only depends on the distance of our Earth between the Earth and the sun, and also is 1/r. 1/r potential. That means this doesn't actually have the rotation, three-dimensional rotation. So that's the angular momentum is conserved charge. And the angular momentum, that means fixed position and first momentum. Then you know that this system is the angular momentum, the angular momentum, the particle actually on the one plane because there's a particular interaction. And also they have this angular momentum as the conserved charge. And actually because the 1/r potential, they have another rotation, another conserved charge. This may be not very familiar with you. Actually, longer the first one who gave this particular conserved charge. This is enough to solve this one. That means we know that the orbit is circle or elliptic circle or some kind of the if you use this one, I'm not where can we speak， 或者是行星走的那个轨道。那么 only have this exact solution can prove the Kepler-3 theorem. And another example is the Schrödinger equation, the quantum mechanics Schrödinger equation for the hydrogen atom. We know all the solution. And then this actually gave the fundamental of the spectrum of all the systems, spectrum for all the atoms. Another one, maybe if you start the mechanics, static mechanics, very important one is 2D IC model, because this has a very below to the quantum integral system, actually exact results can give the, if it takes the size become very large, you can know that actually this system have this thermodynamic phase transition. Without this exact results, we cannot believe that everybody, I think, cannot believe that is true for the static mechanics and also quantum mechanics and Newton series. So exact solution actually gave the stand. So I try to use the Chinese to 给一个基准，所有的东西都是给一个基准。那么现在很多东西呢，实际上只有你有严格的解，才能可能给出这样的基准。那么如果没有前面这些的解的话，大家不会相信这些理论是正确的。好 ，actually they have not of other examples. Actually, for the quantum integral system has many application in the strain gauge series. I think some people talk about ADS, safety correspondence, that actually quantum integral system have many application in this one. And also supersymmetry Yang-Mills, because the non-abelian Yang-Mills series actually is interaction systems. For the quantum case, if the supersymmetry is very high, then this system we call it integral system. because some sector you can use the quantum integral system to get the result of that. And also the static mechanics. And the quantum integral system, the first one actually is start from the IC model. I think also this is become a small area of the physics and also mathematics because the static mechanics. And also they have another models can solve. And also they have the application for the constant metaphysics, actually mostly in the 1+1 space and times. So very famous one, the supersymmetry TJ model, relate to high temperature superconductivity. And also the Hubbard model. I think it is most popular constant matter physics is Hubbard models. And also because the system, if the quantum integral system conserve charge relate the symmetry of the system. So actually, for the quantum integral system, they have many very large symmetry. That means they have some relation with the group series and the extent of the group series. So they have the actually the study of the quantum integral system at has given very important influence to development of the quantum group and represents 表示理论 and also have some application for the algebraic topology, and also in I think 10 years or 15 years ago, the very popular one is non-commutative geometry. Actually, is related to the quantum integral system. So this system is integral system. That means is of course this system is the a strong copying system, and this system because they have a lot of symmetry and can exact solve. Actually, here because it can exact solve, that means you should have developed many methods to solve this system. In history, actually, the first one to solve this is the Hansen Bate. Actually, he's a Nobel winner. So that solved the system. I will give it as this example to give all the method how to solve the system. So so after his work, people call all the method to solve this quantum integral system to beta ansatz. And very important development in this small area is that the 17th, let's give the Australia mathematicians, Roger Baxter, he found actually all the quantum integral system spectrum, the conserved charge spectrum have some universal structure. This actually relate to the symmetry of these systems. And a very important development is from the Fadiev group. Actually, they invent a very popular, very powerful method to solve all the based on the Yang-Bass equation integral system. This method actually is the most powerful method. And also after that is happened in the end of the 1917s, And after his work, almost the embassy solved the integral system can solve to use this method, and also found that they have the exceptional one. This exceptional one actually cannot solved by the older method. This is three method. And all these three methods actually based on a very technical one. They're based on very, the special structure. Should have some reference state. That means they should have some U1 symmetry. This is related in constant matter physics. That means the quasi-particle number should be fixed. That's the so this system you can decompose the whole Hilbert space by the number of the quasi-particles. Because they have the U1 symmetry, this number is fixed. And after that, people found out they have the group, and the most important group cannot solved by this three method. In this, people interested in this small area try many ways to how to solve this one. And we are lucky in the 1913, we together with the Professor Yupeng Wang in the Institute of Physics, Chinese Academy of Science, we together to solve that. Actually, we have tried many methods and tried to find a way to solve that for many years. I was the postgrad student start from the 1990, so that means more than 20 years. I only focus on this particular area to try to find a way to solve it, because the Wadia group already developed a very powerful method to solve most of the system. But at that time, we know that exception one, we try to get that. So we are lucky to find a way. This way, about to now, seems to very universal method to solve all the system of the quantum integral system. So I will use the particular example to find out why these three methods cannot solve this one, and why our method can solve that. So that is big. So the first time, so in this in the first lecture, actually I gave the review about this Wadia group to the method. This method and our method, how to solve all the system, and also the system cannot solve by all of these methods. So that means the first is the U1 symmetry system is with periodic, actually is periodic boundary condition. And and another one is the diagonal term. So let's start from our particular example. That is the Heisenberg spin chain. This spin chain actually is the Heisenberg first introduced this system, this model. In physics, that means we start one dimension space. So that's we have the lattice of the size of the n, and each side we have the spin 1/2 systems. Spin, we call it spin. To try to explain the magnetics in solid systems. And this system, from the bulk interaction, you know that they have the rotation around the spin, around the direction, three direction, because the coping is same. that means you can any choice x, y, z. If the rotation, that the interaction except the boundary. In both cases, they have no change of the interaction. And if you impose the periodic boundary condition, that means you join the beginning and the end together. This system also, this particular boundary condition means that this system also have rotation around 3 directions. So that means the total angular momentum is conserved charge. If you choose z direction, that one, the total spin in the z direction is good number, quantum number. That means this is fixed, cannot change. So if the Hilbert space, you can decompose in terms of this total spin. In each subspace, you can diagonalize this Hamiltonian. Actually, this Hamiltonian have even more conserved charge and a very powerful method. So here, besides the total angular momentum, and they have a lot of conserved charge. Sorry. So here I didn't give the give the expression of all the conserved charge. Actually, because this is a quantum integral system, you can have the standard way to construct all the conserved charge in the following way. So the conserved charge, commute conserved charge, that actually is the abelian conserved charge. You can use another generation function in this small area we call transfer matrix. That's the generation function. You can give the function and as the function of the u, and the coefficient actually is all the conserved charge, all the operator in our Hilbert space. So if you know that, you expand of the with the u, you get all the coefficient. And if you use a conserved charge, you can use this define the generation function. This nothing, this equal each other. And for this particular Hessian spin chain with the periodic boundary condition, you can in particular way to construct this one. Actually, we can introduce, you don't need to consider the detail. I only explain that you can stand a way to construct all the particular conserved charge. In this way, the technique is to introduce some particular matrix, this 2 times 2 matrix, and this matrix actually each element is operator. It depends on the spectrum. Depend on this particular parameter u. In this small area, we call it spectral parameters. And how to construct that way? We start from a particular R matrix. This R matrix first found by the Professor Yang. Actually, he gave the very important contribution for this small area. I try to use Chinese to speak very 更准确一些。杨先生在他的在清华的纪念他的在物理各个领域的贡献的时候，他应该做了一个水晶的一个12面体，里面呢，当然他有非常多的贡献。至少在 mathematics physics 这个上面，他把杨马斯方程是作为他自己的一个贡献刻在上面的。那么这个 R 矩阵呢，最早就是杨先生给出来的。那么 ，so you don't need to go the detail about how to construct in this particular one. So start from a particular Yang-Bass equation R matrix. You can construct this particular matrix, and A, B, C, D actually is the operator depends on the spectral U and on our real Hilbert space. And build up, so you just know that it's enough. That this R matrix is not arbitrary R matrix, two-body R matrix is particular one. That. So how to construct this one? If you, so very important one is that. So we know that our Hilbert space is the lattice, and the size number is n, large n. Actually, this n is a very small one. So for this R matrix is depend two parameters. Actually, I should mention that. Actually, the zero space is the two dimension two space Hilbert space. Actually, this from the zero space you can decompose this two body one as the for 2 times 2 matrix, and each J corresponds to another 2 times 2 on particular Hilbert space. Let's start from the 4 times 4 matrix. That is first one gave the Kimyeong. So you can decompose this 4 times 4 matrix as the 2 times 2. Each one is 2 times 2 matrix. And this actually is action on the Hilbert space of the 2 dimension. That is correspond to AJ, BJ, CJ, DJ, action on this particular Hilbert space. And then because the structure of the monogeometry matrix, the whole space is actually 2n times 2n Hilbert space. And each subspace, each side, we have the 2 dimension 2. That's you can use this particular way to construct the capital A, B, C, D start from. So, so for the particular one, if you take the n equal 1, the whole the sides equal 1, we already know that the capital A just this one, and capital B actually this one, C, D is this one. So for n equal 1, actually we have the A, B, C, D, this one. How to get the n equal 2? So you can use the this structure, you can get n equal 2 case. That means capital U actually you can express in terms of the some operator only on the particular subspace of the J. Actually, this way is the in the mathematics. This actually is coproduct. That means you have the structure on one side, the operator on one side Hilbert space. You can use this way to construct another one on the whole Hilbert space, inside Hilbert space. But most important one is that no matter how many n and how many, we have the spectral particular choice of the number theta depends on each side. So no matter how large of the n, how choice of the theta j, actually because the fundamental one, this 4 times 4 matrix satisfy the particular equation. Now people call it Yang-Bass equation. And because the build-out broke, so let's return to the here. Start point this the R matrix, because this R matrix decomposes of the 2-body matrix. Then this particular choice of this R matrix actually satisfies the Yang-Bass equation, is solution of Yang-Bass equation. If you use this R matrix, use this one to construct operate capital A, B, C, D. I use the coproduct structure to how to construct this A, B, C, D in terms of some Pauli matrix, because in each side you have the two dimension, the operator only for Pauli matrix. So 3 Pauli matrix plus identity operator is all the 2 times 2 bases of the matrix. So that means start from a particular R matrix, you can construct this A, B, C, D. And because this fundamental block of this R matrix satisfies the particular equation, that is the Yang-Bass equation. Use this way construct the conserved charge. Not conserved charge, they commute to each other. This operator commute to each other. Then you expand with the parameter U, you can, the coefficient all the commute to each other. And our Hamiltonian, Heisenberg Hamiltonian plus the periodic boundary condition. This particular Hamiltonian actually can construct in this particular way. That means there is a coefficient of this generation function. That means all of the TU commute with Hamiltonian, because this is just some particular choice coefficient. So that means the Hamiltonian, this way construct the transfer matrix, they commute with the Hamiltonian is a conserved charge. And also each other, this coefficient commute each other. That means all the abelian conserved charge. The proof of this one, you can use the diagram to, you can easily find out a way to how solve that from the particular block. That's actually, we can use the R matrix. The 4 times 4 R matrix can become the two-body R matrix, interaction R matrix. That's we have the this become the let's start one body space-time way is the 2-dimension linear space. So that's R matrix is 4 times 4. You can decompose it as the scatter matrix of the two-body one. That means that you can, this have the 2 index, one correspond the way and another correspond the way. So is the 4, because each of the factor space is the 2-dimension. So the tensor product space is the 4-dimension. That means the R matrix can decompose that one. And this decomposed way actually, just like the here. So the first is corresponding to 1 2-dimension space. J is another 2-dimension space. So from the A, you can decompose as the 2 times 2. And each of the elements actually is the operator action, the J. And the J is 2-dimension space. So that means this actually, each block is 2 times 2. So in this way, you can use this diagram to stand for this R matrix is 2-body scatter matrix. You can think about that as that one. The Yang-Bass equation actually is that. So that means you can, here the 3 R matrix, they satisfy some product. And the Yang-Bass equation means you can move this 3 line in this way. So this means this is the standard to the Yang-Bass equation. So This actually is the Yang-Bass equation. You can use this way to stand of the Yang-Bass. The rho is just a move to this line to in this one cross the R matrix. Then you found out actually only for one Hilbert, the space. If you have the n space, this corresponds to our T, that is capital A, capital B, capital C, capital D. Actually, the action on our real Hilbert space. So RTT equal TTR, actually you can use this way. The first line, you can move to here, then you can move another way here, then finally you can move all the operate in this way. So this corresponds to the proof of the so we start here and we finally we get this relation. This relation can use the diagram from here, end of here. And this equation guaranteeing that the transfer matrix actually commute each other. That means we can expand this transfer matrix as du, you can get all the conserved charge. And finally, because this T actually have this kind of relation. That means the operator capital A, B, C, D actually satisfies some relation. This relation, I gave some of that one. That is A over A commute to each other, over B over C commute to each other with different choice of the spectral parameter. And A and B, D, they satisfy this kind of the exchange relation. From this relation, you can construct all the spectral eigenstate and eigenvalue of the transfer matrix. This way actually is a method developed by the Baulieu group in the end of the 17th. And because this system have the U1 symmetry, that's the total spin Z direction actually is conserved charge. We can decompose the whole Hilbert space in some sub-Hilbert space. Actually, we can choose the particular state. That's all the spin. Each side is spin up. So we call this omega, all the spin up. You know that the SZ action on this all the spin up, that this is eigenstate of the total spin Z direction is the 2n/2. And this state, you can easily find the capital A as the operator action is the eigenstate with space. That means M spin. So the total number of spin of the M can flip down. This subspace can use this the B action, M, B action on this particular state. And you will find the SZ action, this all no matter, we introduce the parameter lambda 1 to lambda m. Actually, particular different choice of the lambda, you can give different state, different states, but all the states in the same subspace with total number of the spin is the 2n/2 minus m, this subspace. The dimension of this subspace actually is the CNM. And you can find out, use the exchange relation of the A and B, D and B, you can find out that for general AU action, this one actually they have this two term D action on it also have these two terms. You can easily to get the action of the transfer matrix on this particular state into these two terms. Because the lambda, different choice, the lambda give different state. So if you choose the lambda in this particular way, this is called the beta ansatz equation. If you choose in this way, the third term actually vanish. That means the transfer matrix actually, this particular state is the eigenstate of the transfer matrix, because transfer matrix is concept charge generation function, abelian concept charge generation function. That means they can simultaneously to diagonalize. So that means if your choice this lambda j satisfies the equation, beta ansatz equation, that this state actually is the eigenstate of the transfer matrix. And the most important way results is that actually the eigenvalue can be right in this particular way. And this Q actually is the polynomial of degree of M. And so from the constructor, that's the eigenvalue or transfer matrix parameterized by some Q function in this universe relation, call it TQ relation. And this function, this polynomial lambda j, the rows should satisfy some particular equation. Actually, so the polynomial, we know that polynomial is parameterized in this way. First, for me, I think it's very strange, because the polynomial, we just choose the coefficient or itself, the rows, then we can determine the polynomial. But here, use the particular way. And also this way plays some universal role in integral system, the concept charge. And actually, this way, here I gave the example to use the particular construct, the eigenstate. And use this way, you can easily find out that actually the eigenvalue can be used this way. So actually, for this particular system, first solved by the Hansen beta, actually, if in that time, why Hansen beta to give this result actually is based on the first I think I told you the integral system, the picture. That means if the system is integral, then that means you can use some kinetic transformation for the dynamic systems. That's the kinetic transformation to the factorized becomes some kind of the free particles. Free particles, we know that is some kind of use the这个结构呢，就是实际上在刚开始，它只是看不同的模型做出来，结果都是这样。这个一定隐含了很多的结构在里头，很多的。而可积系统是一个非常特别的，我用中文来讲吧，因为大家都是都能听懂英语的话，我讲的不一定非常的准确。把这思想，我想把思想给大家讲出来是更重要的。技术性的东西，也许你可以跳过。如果你感兴趣，你再仔细的去把它去关注一下它。那么这个最重要的，我想最重要的是一种思想。那么 Baxter 呢发现了它这样的一个结构以后，他告诉所有的可积系统，就 SU 二代数有关的，它应该都是这样的一个结构。后来呢，很多人 都是想的应该是这样。法蒂耶夫学派给出来的代数贝纳子方法以后，你去解出来，它一定是这样的一个结构。那么它的结构呢，就是刚才我虽然是做了一个例子，那么它严格的依赖于这个问题，就是它把它所有的本征态，在一个子空间上，因为它有 U1 的这个对称性的话，它在这个子空间上呢，它可以用一个参数，用 m 个参数把它描述出来。那么这个 lambda 取任意值的时候，把这个自旋是n 减 m 的这个子空间全部的都张满了，这些态都把它张满了。那么也就是说，我用一组参数把它的本征态在这个子空间的本征态能描述出来，而且呢，我这个transfer矩阵作用上呢，它是一个很特别的一个结果。那么我很容易就选择这个参数满足一个方程的时候，就是它本征态。这个是足够聪明的，就是我们一个 m 乘 m 的一个矩阵，我们找它的本征值。找它的本征态和本征值这两个是相关的一个问题。那么这种方法做的关键是什么？我猜到它的本征史是长得什么样子，我可以用一组参数把它描述出来，然后我把这个矩阵作用上去，我去看这个参数满足什么条件下，就是它的本征态，那么你也就给出来本征值了。这个是足够聪明的，对吧？如果这个 m 大，我们这里面碰到的是2的 n 次方乘2的 n 次方的这样的一个矩阵，你几乎随这个 n 的增大的时候，你几乎不可能，你没有那么聪明来做到它，而你只可能用它的对称性来做。那么这个情况做的时候，因为它有这个总自旋的角动量是守恒的，总角动量是守恒的，我可以用角动量 z 方向，我可以把它分成一些子空间，在一些小的子空间我也来做。但是这个 m 确定的话，这个小的子空间呢，就是牛顿二项式的那系数 Cnm。那么这个 n 和 m 都非常大，对应的这个数也是一个非常大的一个数。那怎么猜到这个？对 U1 对称的系统呢，它可以用这样。那么贝塔最早做这个的时候，它基于一个，也就是说，它一定需要这样的一个总自旋朝上的这个态作为一个基础，这个把它叫做 reference state。那么我去翻转它，那么一个 b 作用上去就有一个位置翻转，然后前面再加一些这些所有可能的线性组合。那个 m 的那个呢，也就是有 m 个翻转，那它的 choice 就是 Cnm， 然后把这所有的系数进行一个特殊的组合，就能给出来。那么这个东西当 m 和 n 非常大的时候，你是没有办法猜的。那么唯一就是因为它这个出发的这个 R 矩阵呢是满足杨巴斯方程，然后我构造出来这个大的 T A、B、C、D， 它满足一个朴实的二次关系。那么正是由于这两个性质呢，就可以使得你把这个构造出来。构造出来以后呢，那么从这儿已经马上就完了，时间也差不多了，马上就完了。这里面我只告诉一个大家，那么从这个结构上来看的话，从构造的话 ，lambda u 是一个 n 阶多项式 ，n 阶多项式我只需要它 n+1个系数就知道了，对吧？而这个多项式呢，它 leading term 最高阶的是2，从它的构造就可以看出来。那么实际上需要 n 个条件把这个多项式就能定出。而这种方法呢，它是根据技术性的一种办法。虽然这个设计的空间都是为数非常大的，但是它有一个规律性的构造出来。我这个大 A、大 B、大 D、大 C， 我的态呢也可以通过特殊的情况。那么这种技术方面找出来以后，发现呢，它可以用这样的一个朴实的形式表示出来。那么这种表示形式呢，当然后来大家都叫的 Baxter PQ， 实际上这在高能理论里面有特别是跟可积相关的一些里面，它都会出现这样。那么这样的结构呢，当然 如果你是第一次碰到这个的时候，你肯定觉得这个很奇怪。对于我个人，我自己第一次看到它，我也觉得很奇怪，为什么我要用这样把2的 n 次方的，因为你黑布的空间是2的 n 次方，所以用2的 n 次方的这样的 lambda u 呢，用这样一个看上去非常奇怪的一个形式把它参数化。那么它参数化的这个参数呢，就是 lambda j， 它必须是这个方程的一组解。那么给出这个方程 m 个的是 n 个未知数 n 组方程，你给出一组解以后带进去，就给出一个 lambda u， 所以把 lambda u 用它来参数化。那么能量的话，刚才我们是劳格导数，那这组解你找出来，那么对应的能量呢也就会找出来。那么这种方法呢，我们所有做的问题不是一个非常一个 particular 的一个 n 或者一个非常一个 m， 而是任意的 n 任意的 m 都能把它讲。那么这是刚才周期的，我下面一个更快一点的来讲另外一个模型。我把这个链呢拉开，原来我是把手跟尾粘起来，这是一个周期的边界条件。现在呢，我把它不粘，就是拉开的。那么体内的相互作用还是这样的形式。那么我给2个边上加2个磁场。那么磁场呢，我都是这2个磁场是平行的磁场。那么这个就是最一般的这样的一个模型。那么为什么是这样呢？因为体内它是可以三维空间可以转的，那么也任意的转动它 SU2 的转动它都是不变的。那么也就是说，我可以把这2个平行场呢，这帮这个我选的转成 z 轴，沿着 z 轴。那么另外一个跟它平行的一定也是 z 轴。那么这个是最一般的2个平行场的情况下，主要是因为它体内的是3个方向呢，相互作用的系数是一样的。那么这个是最一般的，这个系统也是可积的。那么这个证明它的可积，就是我要找到一个abelian 的 conserved charge 的它这样的一个伸长函数。那么这个呢是在88年 ，Scanning 是法列夫的一个学生，现在是英国皇家院士。那么他找到了一种方法，这个方法呢实际上就是他们方法的一个推广，把它解出来了，发现它的谱呢和刚才是一样的，只不过是 A 跟 D 改变了，这是因为开边界的原因。还有一个呢，对于这样的一个系统呢，你去看它的对称性的话，你很容易。虽然这2个磁场加上了平行的，原来体内是3个方向任意的旋转都对称的，现在呢它是平行的，我把它放在 z 轴，那也就是说它 SU2 的对称性现在 broken 到绕着 z 轴旋转的时候，这个哈密顿量是不变的。刚才的总自旋 z 方向的这个分量呢还是守恒量。那么用这个守恒量呢，我也可以把黑布的空间跟周期一样，把它用那个 m 来参数化。那个 m 整数的话，代表是总自旋是2/n 减 m 的这个子空间，我也可以把这个所有的本征解出来，给出来。它可以也写成这样，这个呢实际上是跟它的优异对称性是有关的。然后呢，这时候也是用这样的一个多项式来把它参数化的。这时候的 lambda 呢不能是任意，必须满足一定的方程，就是后面的 BA 方程。那么有点超时了，我把这个上午的这个解的这个结果呢总结一下。细节你不需要知道，因为这个需要一些技术性的一些东西。但是结论呢，就是只要这个系统具有优一的对称性，它告诉你呢有一个 m， 这个 m 代表的是总自旋的 z 方向，同时呢它的原激发呢实际上就是 Maglow 的激发，它代表的是翻转。如果用刚才的那个 picture 来看它的话， reference state 代表所有的都自旋是 朝上的。那么这个 M 呢，就是告诉你了，我把 M 个翻下来，它进行一定的组合，它就能把这个整个的这个子空间都能张成。在这个子空间上，它的守恒量的生成函数的谱呢，这特殊的守恒量的这个生成函数的谱呢，它都可以用这样一个参数化把它描述出来。描述出来呢，这时候呢，它的 lambda 这个 Q 的这个根呢，它必须满足一个特殊的方程。这个方程从这个结构上来看的话，如果没有这个方程，这个是有歧义的。但是这个方程呢，保证了这个是一个多项式，那么不会出现歧义。那么我们构造的时候，这个 transfer function 本身就是多项式。那么这个方法得到的这个解呢，是跟它的可及性是有关的，而且出发就是它的所有的守恒量的生成函数来给出来，所以只有可及系统才可能有这样的情况。而可及系统呢，它的谱呢，又可以用这样一个谱实的关系把它描述出来，至少对于 U1 对称的。刚才那个系统我们可以看到它的角动量的 z 方向的总自旋它是守恒的。这个守恒呢，就刚才我讲的那个 M 呢，是代表翻转的个数，翻转了多少个。那么这个呢，它对应的，如果你让这个 n 趋向无穷 ，M 也趋向无穷，你去看它的基态的时候，它的基态呢，在反铁磁的时候的基态的 M 呢，就是2分之 n。那么呢，总自旋是等于0的。它的激发呢，就是有一个翻转的。那么这个刚好就对应的翻转的产生了一个翻转，我们把这个产生的这个准激发的这个呢叫做 Mangalore。那么 M 的不同代表了 Mangalore 的个数的不同，所以这个系统呢一定是总自就是离子数守恒的这样的系统。那么我稍微把下午要讲的这个系统呢，刚才周期的我们知道它是具有三维空间的旋转性，对于这样平行场的时候呢，它就具有绕 z 轴的这个对称性。那么这个都保证了我们会出现后面的 Mangalore 的激发。那么 Sciani 呢，在88年他证明了，对于这两个边界场，你可以取任意的，不一定平行，任意的两个边界场的话，对于这个系统都是可及的，可以找到它的守恒量的阿贝令的守恒量的生成函数。那么88年的时候，他给出来这个解的时候，他当时就意识到，如果这两个场不平行的话，是没有办法用他们发展出来的这些方法都要解的。所以从88年之后，这个小领域里的人都希望寻求一个办法，能把这样的可及系统也能解出来。那么这个如果不平行，大家很显然，你绕着 z 轴的这个旋转对称性也是没有了。那么这个系统怎么样呢？来解呢？那从88年之后一直到13年之前，没有人给出了一个正确的解。有人号称给了解，但最后大家都发现他的是错的。他只可能在某些特殊情况下，这个 n 和 m 是特殊值的时候才是对的，其他情况都是错的。那么这个问题呢，也就是我是从90年开始做科研的，那么从那时候我一直在做这个领域。实际上早期在90年，在80年代到90年的中期，实际上是非常热门的，不光是在咱们国家，在整个理论物理、形式理论这些都是非常热的。那么回归到科研，我们很幸运的在一起。那么实际上在这些年在国外，他在国内虽然有很多的行政的任务，但实际上他一直也在探索这个问题怎么样解。那么刚好我们很幸运，我09年回到国内的，那么我们开始一起合作，那么最终我们把这个问题解了。那么解呢，实际上有些在这里面我讲它的没有讲细节，但它解的结构里面有些引申出来的，它就是一个多项式。 后面我们找到的方法就是用多项式的分析可以把这个问题求解。那好，那时间没有控制好，那么非常抱歉耽搁了大家的。我希望呢这样的一个东西呢，把思路给大家，因为这是一个非常 technical 的一个东西，希望思路能给大家。好，谢谢大家。
好，非常感谢杨老师给我们对这个 algebraic balance 这个方法一个非常清楚的介绍。大家还有没有什么问题要问杨老师？
老师，非常感谢您的讲解。就是我更关心这个可及系统在超对称理论里面的应用。就是我之前看到就是这个和塞伯格韦特理论有联系，但是我不太清楚这个具体的联系是怎么样的，以及就是在比如超对称里边的可及系统的话，这会不会出现像杨 Baxter 方程类似的东西？
是的，它有可能还突破这个。那么刚才我讲的一个例子就是比较高的超对，特别是 n 等于4的4维空间的样面式理论 SUN 的这样的一个，它有两个方面，一个 SUN 的这个 n 非常大的时候，它会出现可及只落在平面的这些图的话，它的可及。那么它对应的里面呢，因为纯的仰面色理论实际上它是一个没有质量的，它是可以量子意义下是都可以可及的，对吧？它里面的反常维数很重要，它的反常维数最终可以刻画成这些杨巴斯可及的自旋链的一个它的谱的问题。这个是跟它是有，我对这方面设计的并不深，但我知道这个肯定是一个重要的练习。
塞伯格韦特是 n 等于2的
啊，
对 n 等于4，但是有一本塞伯格韦特的可及性其实已经研究得很透彻，有一本书叫《塞伯格韦特 Theorem and Integral System》，你可以找那本书来看。
你可以找那本书来，这个是比较成熟的。我这个设计的自旋链的这部分是后来弦理论里面也出现，n 等于4的仰面色理论里面也会出现的。
好的，谢谢老师。
大家还有其他问题要问杨老师吗？好，如果没有的话，杨老师下午还会给我们第2堂课。我们再次感谢杨老师。
好，谢谢大家。
谢谢杨老师。
没有，我把时间没
事。因为讲 algebraic balance， 我其实因为我在 Stony Brook 上。 好，那我们就开始下午的课程。下午第一节课是杨文礼老师继续给我们讲 Quantum Integrable Systems and their Solutions。大家欢迎杨老师。
好，大家下午好。那上午呢，我主要是介绍的实际上主要是沿的。就是法蒂尔学派大概在在70年代末，他们发展的一套系统的办法。这套办法呢，实际上大家可以看到前面的实际上那是从 R 矩阵的一个特殊的一个解，杨巴斯方程的一个解出发，那么构造了一个多体系统。这个多体系统呢是近邻相互作用的，然后呢它具有非常高的对称性，那么也就是说我们可以构造出来一个它相互对应的一系列的算子。那么我们的哈密顿量呢，可以通过这些相互对应的这些算子来构造出来。这样呢，进一步说明这相互对应的这些算子呢，全部都是我们这个如果以这个哈密顿量为演化的过程中的守恒量，那么这些守恒量呢是相互对应的。然后这套方法呢，它隐含的有一个性质的，它必须有一个优一对称。那么这个优一对称呢，刚好就通过这个优一对称的它的本征值，把黑布的空间分成一些子空间，每一个呢，它的穿梭矩阵的谱呢，在这个子空间呢，都有一个谱实的一个描述呢，这个谱实的描述呢，就是 Bax， 后来大家都把它叫做的 Bax 的忒后关系。不管你是只要你这个系统它隐藏的这个结构对称性的这个结构是由跟 SU2 代数本质上讲应该是 affine 的 SU2 代数相关的话，它都具有这样一个特点。那么是否所有的这个 SU2 代数所对应的这样的系统呢，它的穿梭矩阵呢，都是具有这样谱实的结构？那至少在优一对称破缺另一类知道之前呢，大家都发现，你不管是不同的系统解出来它的谱呢，都具有这样的一个结构。那么是否这个是谱实的呢？后来特别是在88年的时候，我第二个例子讲的是我通过边界场，我加进去的边界场，使得把原来的 SU2 的对称性破缺到一个优一的对称性，还是保留了原来的优一对称性的时候，这个系统都可以这样来解出来它的谱，具有谱实，这都具有 Bax 的这种 TQ 的谱实的这种刻画。那么这个刻画里面呢，刚才我说的总自旋 z 方向分量的一个 m 的这个子空间，这个 m 呢可以到 n 趋向无穷的时候，它的原激发呢就可以看的是一个离子数的一个表象。那么这样的系统呢，就对应的离子数守恒的系统都可以用这样办法来做出来。那么是否所有的可计系统都是这样的？那么在88年斯克亚内的这个工作出来以后，大家就加边界场。那么通过边界场加任意的边界场保持它的可计性的时候，发现如果这两个场不平行的，那么自然的平行的时候 SU2 退化到了 U1 绕着 Z 轴的这种连续的旋转的对称性。那么如果两个场不平行的话，那么它一定把这个U1 对称性也破缺了。这时候你用原来的这样来描述它的话，离子数是不守恒的。那么这样的系统的解会是什么样的？那么从88年之后呢，大家就知道这个实际上有非常多的一类都是这样的。那么这个系统怎么去求解呢？那么沿用前面3种办法都是做不到的，这个是做不到的。这个经过了实际上88年到13年30多年的时间呢，大家都尝试了，没有办法来解它。那么要解它的话，我们刚才实际上我已经上堂课的时候我提到了，它实际上做的这个办法，包括贝塔最早用的办法，实际上本质上就是我们刚才讲的，我把它这些本征态呢，用一组参数化参数， 然后我把我要对角化的这个矩阵呢作用在它上面，看它的结果是什么样的。然后这组参数化我如果选得好的话，刚好就能满足一定方程条件的时候，就是它的本征态。那么这个前提条件呢，要求你足够的聪明，能猜出来它的本征态长得像什么。那么这个东西回到一个 m 乘 m， 这个 m 是比较小的一个矩阵的话，这个矩阵源几乎没有规律，就是一个 m 乘 m 的一个矩阵，你几乎没有办法猜出来它的本征态是长得什么样。那么有效的办法是什么呢？我们在线性代数里面学的第一个，你肯定是写出它的九七方程，它的本征值满足的一个关系，代数关系。那么这个代数关系呢，刚好是一个 m 阶的一个多项式。你解了这个 m 阶的多项式，你就知道它本征值可能取的值是什么。它本征值一定满足九七方程。那么可能的值，我知道了这个本征值以后呢，我去找这个本征相应对应的本征态，这个是最有效的办法。在 m 乘 m 的矩阵 m 不大的情况下，这是最有效的办法。这也是我们线性代数，我想它发展出来，现在所发展出来所有的办法，这个是最有效的。那么经常我们碰到的，不管在零级态、在可及系统碰到的，这个 m 是等于2的 n 次方乘2的 n 次方，那么这个几乎是不可能的。随着这个 i 是这个 n 增大的话，这是一个指数增长的一个数，对吧？在10级以上，我现在直接对角化能做到的了不起，你利用它的一些对称性，了不起做到20，再往上，现在所有的计算机都做不出来。那这是说明了 我们要得到的结果是 n 加阿伏加多罗常数这个量级的。所以这个东西呢，那我就要发展成另外的办法来做它。那么刚才讲了，实际上在代数贝塔那之前呢 ，Baxter 发现了它 lambda of u 这个函数呢，它有个朴实的结构，至少在由于对称这样的系统里面，它有个朴实的结构。那么我们就在受到上面的启发呢，我们来看它的这个。我们知道它的本征值是一个 n 阶多项式 ，leading term 是知道的，它有 n 个系数是不知的。那么对应不同的本征值的时候，它这 n 个系数是不一样，给出来不同的多项式。它多项式的个数呢，如果把相重的谱都记在里头的话，它就是2的 n 次方个。那么我们能否看出来、找出来这 n 阶多项式的一些关系，我能把这个多项式定出来。那么这个是源于我们刚才的九七方程，它的本征值满足的关系来确定它。这个是我整体的我们的思路是这样的一个思路。这个问题呢，实际上是把一个指数增长的一个需要确定指数增长的这样的一个问题，转换成一个 n 阶多项式前面的系数 n 阶的一个问题。如果这个关系是一个非常复杂，我们几乎没有办法求解，那这个方法是没有意义的。那么幸好仰巴斯可积的这种系统，它确实有这样的。那么整个事情呢，我们是基于这样的问题来做的。那么要做这个问题呢，实际上我稍微把上午的结果回忆一下。那么这个还是用最简单的一个例子来说明这个问题。那么就是海森罗斯自旋链。那么两种，一个是优于对称的，一个优于不对称的，我们来看呢，它是什么？它的解。那么另外一个后面再进一步的走的话，我们是希望让这个 n 非常大。优于对称的这个系统的话，前面的这个解，它可以让你分析 n 趋向无穷的时候，在某些特殊的态，在基态和低能激发的这些态的性质都是可以研究的。那么如果我们给出来的解能否也做到这一点，那就是第二部分要讲。好，那么还是回到刚才上午讲的一个简单的例子。那么这个例子呢，这系统就是近邻相互作用，格点上只有近邻相互作用，它3个方向的耦合都是一样的。然后我加进去这个边界条件，第一个是周期边界条件，那么这个不破坏 S 空间3维空间的旋转的对称性，那么这个自然具有绕 Z 轴旋转的这个对称性。这个的谱呢， 你不管用什么样的办法去做的时候呢，只要是你用一种特殊的办法，就是从 R 矩阵的一个解，那么这个解呢就是游离解，这是杨先生最早给出来的。从它出发，那么它有个构造出来这个 transfer 矩阵的 transfer 就是刚才像我写的大 A 加大 D 的话，我们知道它是跟哈密顿量对应的，也就是说它是一个守恒量的生成函数。那么自己又是对应的，那么它所对应的它的系数呢都是相互对应的。那么总自旋呢也是跟呢 z 方向也是，这是它的优一的对称性。那么这个系统呢，刚才我们像我们用一种方法给出来的解，它的穿梭矩阵呢，这个 TU 的本真值呢，可以表示成这样的一个普实的关系。那么这个关系里面，这个 Q 呢是一个 M 级的一个多项式，它的根呢满足这样的一个方程。那么这个当然刚才讲了，这个 M 实际上是跟它的总角动量 z 方向的本真值是有关的。它的 M 是从0到大 N， 它使得呢黑格尔标志的黑格尔空间的维数呢是 C 那个牛顿的那个系数 Cn 取 M 个它可能的值。那么第二个例子呢，实际上就是我们来看呢，就是我通过边界场，两个边界场如果不平行的话，由于体内的它这个是各项是同性的，你三维空间的转动呢是不改变的这个耦合的，唯一可能改变的是后面边界场。那么这时候呢，我可以先把这个选择，使得第一个格点上的这个磁场绕着 z 轴，可以旋转把它选择 z 轴。那么在绕着这个 z 轴旋转的时候呢，第二个场跟它不平行，那它一定有夹角。那么用这个旋转，我总可以把第二个场旋转在 x 和 z 的这个平面上，这个是总是可以做到的。那么 x 分量呢，由于它不平行，它必然有一个科塞，这个科塞标记的这两个场之间的夹角，科塞等于0，这个就是平行场，就是我上午讲的第二个例子。那么科塞在非0的时候，它就是表示这两场非平行的。那么这个哈密顿量呢是最一般的加两个边界场，而科塞非0的时候，这个系统呢，它一定把刚才绕 z 轴旋转的这个对称性是破坏了。那么这个解呢，当时这个解实际上最早 Scanlon 就给出来了，他知道用这种办法是没有办法，用前面他们的办法是没有办法解的。那么证明它的可及性呢，跟刚才一样，刚才我们是从一个 R 矩阵，这个 R 矩阵是杨巴斯方程的一个解来构造出来的。那么用它构造的这个 block 构造着大 A 和大 B、大 C、大 D 这样的其中 A 加 D 的话，构造的就是我所有的守恒量的生成函数。那么对于这样的一个系统，由于边界场出来呢 ，Scanlon 在88年就找到了，除了刚才的 R 矩阵以外，我还需要两个 K 矩阵。这个 K 矩阵只要它满足反射方程的话，用它特殊的这样的一个形式构造的这个transfer矩阵呢，一定是相互对应的。同样，我们这个哈密顿量呢，就是它的 log 导数在 u 等于0这一点的值。那么也就说明了这个系统是可及的。那么科塞是任意的时候都是可及，但是当时88年它是解不了的。那么从88年之后呢，大家想了很多的办法去解它。刚才我讲了，原来的办法是我猜出了它的本真态是什么样的一个结构，然后我把它做出来的。这种方法对于这样的系统是没有办法做的。那么很多人，包括法列夫学派的人，应该是前几天我碰到 Ristigen， 他是法列夫的学生，他现在是在清华的BIMSA 和Yale Center 都是兼职的，全职的工作的。他是法列夫非常得意的学生，他很早就到美国拿到教授的位置，是非常有名的大学。我记不清楚 Berkeley， 我印象他是很早，后来邱先生嘛，他请过来以后，那么如果大家 有幸去了三亚的就是邱先生在那儿有一个数学中心，那儿中心主要是会议的，它里面有一个数学的大师的一个花园，那个花园里面都请了很多数学大师在那种树，去的人除了瑞士提肯之外，其他都是菲尔兹奖获得者，在那儿种了一棵树。瑞士提肯也是被邀请的唯一的一位在那儿做的。他也想了很多办法。前几年在那儿，我跟他聊了这个事情，那么他觉得这个是非常不容易的一件事情。那么这个实际上现在刚才我给大家讲我们的这个思路呢，刚开始做它的时候并没有这么清晰，只是把它的解做出来。后来回想意思就是刚才的9-7方程是类似的。那么这个问题是什么呢？就是我 transfer 矩阵，它如果作用它的本真值的话，一定是 U 的一个 n 阶多项式，或者是在这个边界的问题呢，是一个2n加2阶的一个具有是相当于一个移动以后是一个偶函数这样的一个系统。那么决定这个多项式的条件呢是 n 加2个条件。我找到这 n 加2个条件，这和我们原来的9-7方程实际上有类似的性质，也就是说我的本真值呢满足一个代数方程，是一个 m 阶的一个代数方程，和这个矩阵的阶数是一样的。那么对这样的一个 Hilbert 的空间是2的 n 次方，但是这个多项式呢是一个 n 阶多项式。leading term 我是知道的，所以它只有 n 个条件。如果能找到这 n 个条件，把它能确定出来的话，那么这就是一个非常好的事情。那么实际上我们就是用这样来做的，因为你这个系统是由 R 矩阵来构造出来，还有 K 矩阵是最一般的解的情况下，我们看到 R 矩阵满足一些性质，那么由这些性质呢，我就可以得到这个 transfer 矩阵呢满足一个性质。那么第一个性质呢，就是如果你把这 transfer 矩阵这个 U 移一个2分之艾塔的话，你可以看呢，它本身就是一个偶函数，作为 U 的函数是一个偶函数。另外一个呢，在0这一点的值呢，我很容易就求出来。那么它的 leading term 呢，我也能知道它前面的系数是多少。所以这个式子呢，就告诉你呢，它是一个2n加2阶的一个多项式。这时候是个算子，如果你作用在态上，它的本真态上的话，它就是一个多项式，那么也就是一个2n加2阶多项式。那么这个条件呢，告诉它是偶函数，就是移以后是偶函数，也就是说它实际上独立的系数呢，实际上是除了一半的。因为一个偶函数，我们知道，如果移动以后它这个是一个偶函数的话，它只有偶数阶的系数是非零的，奇数阶全部都是0的，所以剩下来确定这个多项式的系数呢，它只有 n 个。那么这个是一个特殊的，是2n加2阶，那么除以2，也就是只有一半的系数是非零的。那么它就需要 n 加2个条件。那么另外 n 个条件呢，我实际上也是通过R 矩阵是确定的 ，R 矩阵的性质再加上 K 矩阵最一般解的性质，你可以确定，就能把它计算出来。那么这就告诉你了，这个多项式确定它的条件我也能确定了，这就跟我们刚才9-7方程一样，本真值确定本真值的方程我确定了，我只要需要找这个多项式的0点，我就能确定的本真值。那么这个的问题呢，也就是说，如果把它作用在态上呢，就是它的本真值所满足的方程，这跟刚才那个是一样的。而这个方程呢，是最一般的边界情况下都可以做到的。那么也就是说，这个方程就决定了这2的 n 次方个 lambda u 作为多项式的 lambda u。那么这个 lambda u， 因为前面优于对称的这个系统，如果这 cos 等于0的话，用 scaling 的方法解出来，我们是用 TQ 这种形式来描述，来参数化这2的 n 次方个多项式的。那么我们当时就想着是否能用这个 TQ 这种形式来把它参数化呢？那么参数化的结果呢，你会发现这个方程最一般的，如果用 TQ 这种参数化的话，它只是这种形式，必须要加后面这一项。 这是一个最朴实的对 SU2 对应的系统的话，只可能是这样。那么很显然 xi 等于0的话，这一项是等于0的，那么这一项就没有，那么这就是前面 Bax 给出来的这样的关系，这就说明了这个 xi 不平行的这个参数呢，决定了它必须要有这样一项。那么这一项呢，这个 q 呢，作为这参数化这个 lambda of u 的时候，这个 q 呢，刚才它是阶数是从0到 n 的，它那个 m 那个参数是可以改变的，是一个整数。这个整数刚好对应的 SZ 在黑板的子空间上的数就是2/n 减 m， 那个 m 是一个整数。那么这时候由于优于对称破缺了，所以这个 m 的取值呢，你它不可能是不可能是某一个确定的值，所以这时候的这个 q 呢，它的阶数呢就是 n， 只有一个参数，因为它那个优于对称破缺了。那么对应的呢，我们要求从这个形式来看的话 ，q 肯定是这个 lambda of u 肯定是一个分式的，不可能是一个多项式。那么要求这个它的0点呢 ，q 多项式的0点呢，也就是对应的这个的极点呢，它的在这个极点呢，它的流数呢必须是等于0的。那么这个就给出来一个 BA 方程。那么这个 BA 方程呢，就保证了它是 lambda u 呢是我们确定的多项式，而且呢，这个方程呢，就是上面它的，我们把它叫做在这种情况下的一个9-7方程。那么这个9-7方程这一般的解。那么这个问题出来以后，我们在 n 小的时候直接去验证它，把它所有的谱都找出来了。那当然一平行，这个回到的就是 Bax 的 TQ 关系，所以这个是一个最朴实的一个关系。那么下面的工作呢，就是说我们知道本征值我知道了，那本征态怎么样构造呢？那么这个就相对来说就容易得多了。那么由于我们前面的这个工作呢，那么本征态的构造呢，是依赖你选的这组基是有关的，对吧？如果你选的这组基就是本征态的话，那自然它就是对角的，这矩阵就变成对角的。所以在一般情况下，跟你这个基的选择有关。那么这个问题，只要本征值知道，你线性代数里面你知道了本征值再找本征态，这个是一个非常相对来说简单多的问题。那么这个我们通过一些技巧呢，实际上是可以把它的本征态来构造出来。这个对不起，这个是我翻多了。那么它的本征态呢，构造的形式呢，和原来的结果是很像的。原来是在一个态上，这个态还是刚才那个态，但是作用 n 个 b， 这个 b 呢，它不是刚才的每一个 b 呢，就是一定翻转的一个。这个里面呢，有翻转的，有没有翻转的。所以呢，但是参数化它需要 n 个，这 n 个呢，跟刚才的 q 这个多项式，它的根是有关的，有 n 个。那么作用的结果是这样的一个结果，这个结果是严格依赖于我们这样给出的 TQ 的，完全可以，你可以证明，把这个穿数矩阵作用上去以后，就能得到这样的一个结果。那么这个某种程度上是知道了本征值以后才能得到这个，没有本征值的结果，这个是不可能得到的。好了，那么也就是说，我们能把本征态、本征值都能做出来。那么下面一个问题呢，这是我要做的第二部分。第二部分呢，我们是希望考虑这个 n 非常大，因为这个模型的提出本身，海森堡最早在上个世纪20年代，他提出这个就是为了解释在固体里面磁性的问题。那么这个磁性的问题，那对应这样的一个宏观的系统的话，它那个 n 的量级是阿伏加多的常数的，所以我们希望要考虑你这个问题。我刚才的解是任意的 n 的情况下，我都能给出来这样的解。那么下面就要考虑这个 n 非常大的时候，这个问题特别是关心的物理关心的是在基态 附近的这个性质能否分析，就是刚才所说的贝塔上方程。这个 BA 方程的解，我在 n 非常大的时候是可不可以做到？然后呢，在 n 非常大的时候，在基态和基态的低能激发上，我能否把这相应的 lambda u 的性质能决定出来？那么这个就是后面，那么对 finite 的 n， 我们这个用现在强大的数值办法都能做出来，10级以内的都可以把它做出来。那么回到刚才的优于对称的系统，那么第一个周期边界条件和2个平行场的情况下呢，它这时候呢都具有这样的一个对称性。那么它的谱呢，我们讲呢就有 Baxter 的这种谱实的这样一个 TQ 关系，没有第三项那样的一个关系。那么这个方法呢，实际上在很早，杨振宁和他弟弟杨振平实际上。我看一下这个上面我没下一页。杨振平和他弟最早是在 Liebling 的系统里面做的，他应该是在69年，我记得我是69年出生的，他们在69年的以后都把这个问题解了，而且这个是一个开创性的。后来所有关于可及系统里面所热力学的分析都是基于杨先生兄弟俩的69年的这个工作，没有跳出这个工作。那么真正的就是对于这个自旋链这样的系统呢，是日本的Takahashi在99年把这个问题写了，然后他在99年应该写了一本书，是关于他的工作。那么这个的最原创的那应该是杨先生他们兄弟俩的工作，所有的东西都没有跳出他们的。那么对于我们刚才这样的一个系统呢，由于它的 TQ 关系多了这一项，它的 BA 方程多了这一项，那么这个能否分析它 n 趋向无穷的时候的性质呢？杨先生呢，就是前面如果 cos 等于0的话，这个都是他发展那套办法都是可以系统去做它的，而且 n 趋向无穷两头是实际上跟咱们中国人的逻辑就无穷。跟太极一样，无穷和少数的2个似乎是一致的。那么无穷的时候是很好解，中间的反倒是不太好解，而两头的是好解的。那么这套办法整个都是通的。后来所有作为可及系统来分析它物理性质的，都是基于前面的办法做的。而出现这个的时候，它会不会？那么这个问题呢，实际上13年我们工作刚出来的。这个小领域就很多人就马上去做这个事情，然后呢，同时也在跟我们探讨这个的贝塔根的分布是什么样。那么想解这个问题呢，实际上思路呢是最重要的，但一直都没有找到好的办法。那么中间呢，我们选了一个，我们认为问题就是解这个 BA 方程。那么这个 BA 方程由于这一项的存在，使得它的求解呢，它的贝塔根在基态的时候，它的分布规律性呢不是那么强。那么怎么样做这个问题呢？当然，我们想到了一个办法，呢就是说，我做这样一个 TQ， 我把第3项本来是必须要有的，我把第3项扔掉，这样一个 TQ， 然后我要求这个贝塔根呢，它这个 Q 的根呢满足，使得它的流数等于0。那么这一定是一个多项式，阶数跟刚才的多项式的阶数是一样的。唯一的在 n 有限的时候，这个肯定不对，这个结果肯定是错的，肯定不是原来的。那我就要看这2个之间的差距是什么。一个呢，就是我用脑格导数算出来的能量和真正的能量之间差距，我让这个 n 大的时候呢，看它们之间的这个差距随着 n 怎么样来变。那么这个结果呢，如果把第3项扔掉，就回到了 Baxter TQ， 那么现成的办法都是成熟的，你可以直接把这个解出来。那么用这种解出来的呢，在有限的 n 肯定不对。 那我们看它呢，随着 n 改变的时候，结果是啥？当 n 非常大的时候，它是衰减下来的。也就是说，到无穷的时候呢，第三项的贡献是，至少在我们计算边界能和低能，就在基态和低能激发的时候，它是有效的，它的近视是有效的。那么这个是为什么？我们到现在也不是很清楚。那么得到这个，并不是说我们异想天开这样去做的，实际上是跟后面其他的，当这个变成各项异性的 z 方向有一个特别的方向的时候，它对应的是 xxz 的时候，这个结构里面它多了一个参数，这个参数刚好就是 z 方向的耦合跟别的方向耦合不同的时候，这时候呢，在那个数学上，这个结构的有量子群，而当这个 eta 取一些离散点的时候呢，这个时候呢，它会出现两项的 TQ。那么这时候我可以分析它，刚好这个 eta 这个离散点依赖于这个 n， 当 n 趋向无穷的时候呢，这个 eta 的取值呢就在整个虚轴上就连续了。也就是说，在整个虚轴三角的时候，在虚轴这个区的时候，你第三项可以扔掉，可以做出来的结果是准确的。那么受这个启发呢，而我们做的这个汉森堡自旋链呢，是没有这样的退化点，是做不了的。所以我们假设这个发现的结果是很准确的。边界能呢，我又可以通过这种办法把边界能算出来，给出一个解析的表达式。那么这个表达式技术上是跟传统的办法，那么得到的结果是它。那么这个结果呢，和直接DMRG 算基态的话，是可以算到 n 非常大的都可以算的。我们用那个解析表达式呢，跟 DMRG 的结果对的话，也是准确的。那么说明我们这样算出来的边界能是对的。但是唯一因为是做严格解嘛，我们所有东西都要逻辑上要严谨的，要严格的，没有跳跃的。所以除了这个结果的对，但是并不代表我们这个方法一定是在这些情况下一定是准确的。我们不知道为什么第三项可以扔掉。那么受了一些启发，可以做到这一点。那么这个去对的话，一个是用 DMRG 的对，还有一个呢，你可以把刚才的 BA 方程，它关于那个非平行的那个参数可塞呢，那个 BA 方程你可以按可塞展开。假设可塞很小，就是近平行的情况下展开。在我们的工作一出来，13年，Rafi 他是迈阿密大学的一个教授，他一直在这之前呢，他一直是在边界可及的方面，他关注很多，大家把他叫做boundary guy。这几年好像我们的他也跟不上我们的，他后来改了，做别的地方的东西了。那么他有一个用围绕论，他做到这个边界能，根据按这可塞的话，它可以展开到4阶，因为它是可塞的偶函数，所以只有偶数阶才会出现，奇数阶都等于0的，所以它 after 可塞的4次方呢，它算了一个精确的表达式。那么刚才我们那个解析表达式展开，按可塞展开到4次方，跟它完全一样。当然我们可以给出来更高阶的展开。那这个结果呢，跟 DMRG 是对上的。那么对上呢，这个并不让我们觉得并不是一个真正做理论的人所能特别是严格解的精确解的这样，那从逻辑上我们并不满意这个结果。那我们怎么样来看这个问题呢？这个问题呢，因为我们刚才加第3项的那个是源于这个方程，源于 lambda u 多项式的性质，它的 n 个独立的系数之间满足的 n 个条件，n 加2个系数满足 n 加2个条件，来给出这个方程的解。我把它参数化，用 TQ 这种方式把它参数化。那么这个参数化呢，就刚好是 Q 函数的0点。那么 Q 函数的0点，当 n 趋向无穷的时候，它是否具有非常好的规律？特别是对一些特殊基态和原激发，它是否有好的规律，我们能把它做出来。 那么这种方法如果退化到优一对称的这种 TQ 是非常好的一种参数化，确实前期的这个经过几十年，大家都已经一套标准的方法来分析它。那么对于这个问题呢，我们试了用 TQ 必须要加上第三项。那第三项以后我去解这个东西，对这个特殊的例子，我把第三项扔掉，当 n 趋向无穷的时候 ，n 很大的这一项的贡献很小，我们认为是对的，就可以把它算出来。算出来以后，跟数值的对于特殊的情况下进行对，是可以对上的。那么扔掉第三项，这个并不是我们从这个模型把它能得到的。那么所有的东西都由这个方程定出来的。那么我们希望呢，刚才是把它参数化，用 TQ 这种方式来参数化。那么另外可以想到的一个参数化，它是一个多项式，它本身的零点是参数化这个多项式最有效、最自然的一种方法。那么是否对这儿有效，这个是我们前期是不知道的。原来的是我把它参数化成一个 Q 多项式。这个 Q 多项式呢 ，TQ 来描述的。这个 Q 多项式的零点，而 Q 多项式的零点在优一对称的时候呢，它在基态的时候和原激发的时候，它的零点分布是非常有规律的。那么以至于我们可以用解析的办法把它做出来。那么对这个系统是否成立呢？这个开始我们并不知道。那么通过分析呢，我们发现这个确实是有效的。那么就是对这个系统的时候，刚才那个系统的时候，如果这个系统的哈密顿量在阿米的这个范围，因为基态的区分，我们必须有在阿米的情况下，它的本能值才可能都是10的，才可能有区分基态和激发态的这个区分。所以我们要求它在阿米的情况下，边界参数取阿米的情况下，我们发现它的零点呢，实际上结构非常的清楚。那么也就是说，它的零点呢是在形成一个旋的虚部是确定的，它落在它的中心实部呢落在实轴上。边界的改变呢，使得它出现了一些边界旋。当然，这个是沿用了 Q 的这个零点，在优一对称的时候，它就有这样的结构。那么这种的结构呢，当 n 趋向无穷的时候，它在这个实轴上的它的实部呢，就在实轴上就连续分布了，而且它可以形成一个密度，这是原来的系统就有的。那么从技术上来讲，这个方法用它去分析的时候，技术上就回到原来的技术。那么通过这样的办法呢，我们把这个问题就直接可以算出来。算出来结果和刚才算的对这个确定的模型呢，我们跟刚才我把第三项扔掉，算边界能算出来的结果完全一致。那么这就告诉了一个什么呢？我把2到 n 次方的这样一个 lambda u 呢，我选择了一组参数化参数来描述它。那么这个在可积系统里面质量非常多的 instant node 的解的ADH 的构造也是这样，都是类似于这样的一个构造的。那么这种参数化要好，是要我们分析这个 n 很大的时候，无穷 n 趋向无穷的时候，你是否还能分析中间的一些态，感兴趣的态。那么对 n 如果是一个 finite 的值的话，我 TQ 已经非常好的。这个是源于这个 idea 是源于原来优一对称的系统，我用 TQ 这样的描述它。而对于普适的这种量子可积系统，现在看呢，似乎它的自己的零点 lambda u 的零点也是一个非常好的一个参数化这个，而满足这个最重要的就是前面的那个9区方程，就是我不管你是，就是这，不管你是用 TQ 来参数化它，还是用它自己的零点来描述，它都是这个方程的解，对吧？ 这个方程的解，而我们刚才所用的零点的这种办法，实际上也就是说，它的零点呢，在 n 趋向无穷的时候，它的结构呢，也是一个非常好的来刻画这 lambda u， 特别是对于基态的时候。那么这套方法呢，实际上不光这个模型，因为量子可积系统它是依赖于 R 矩阵的解，就是杨巴斯方程的解。杨巴斯的方程的解应该在80年代中后期已经进行了全部的分类，它跟量子代数、量子群都是有关的。而它所有的解所对应出来的系统的，它的如果优于对称的时候，它的用 Q 描述的这样的一个系统是什么样的？然后优于对称的系统的话 ，Q 描述的这个你可以去分析它基态 n 趋向无穷的。那么我们这样做的是，我是以一个例子来做的，实际上这个方法呢是普实的。这个普实的呢，我们试了几个系统，我在这儿没有列，实际上我在这儿，这个结果就是跟它对上。当然，你用 DMRG 你也可以基态解出来。那么实际上呢，我这里是以自旋2/2海森堡自旋链来做的。我们这个方法 TQ 的这种描述的话，对于这里面所有的系统我们都做了，几乎所有杨巴斯意义下杨巴斯方程的解的话去做的话都是可以。而且如果破坏了优于对称性，一定要加上第三项，没有第三项，这个结果是肯定是错的，反正肯定是不对的。那么加上第三项的，对于这里面所列的，就是大家所感兴趣的这些可积系统里面，都是可以做到的。我们都试了，所有的都试了。那么用刚才来分析它的物理性质，要计算一些物理量的时候呢，用这个 TQ 呢，对某些模型我们扔掉第三项做的是对的，可以做对，但我们不喜欢这个方法，实际上是有跳跃的，它逻辑上不是一个让我们自己满意的一个逻辑。那么后面这种办法呢是普实的，我们试了自旋为1/2的，自旋为1的海森堡自旋链，自旋为 S 的海森堡自旋链，我相信也是对的。我们用它的零根参数化的话，就可以分析它基态，特别是 n 趋向无穷的时候，它的性质。另外一个呢，我们做了一个这样的系统，就是这个 n 呢最小的一个 nr2的，也是对的，这个没有问题。那么这个方法呢，因为是疫情快完的时候，我们才想到的这样的办法。那么进一步要做的话，是组里面的年轻人他们在试这个，但是从观念上来讲，从我个人还有王老师的我们这个想法，就是在上升到哲学，就是我们一个 philosophy， 我们认为这个方法是普实的，一定是可以做下去，可以做的。那么这当然在这2堂课里面呢，特别下午这个堂课呢，我都是以2堂课都是以海森堡自旋链来做的，介绍我们这个方法。那么重要的是这个方法要普实。那么好，最早是贝塔给出来这个方法，后来呢解它的话，真正把它推广到所有的系统里面，实际上是法列夫学派的这套办法。但是法列夫学派的这套办法虽然普实，由于对称破缺的，它是没有办法做的。这也就是为什么他们苏联人，就前苏联的这些人对我们的工作呢，他是非常的肯定的，因为他们尝试过，一样，大家都是尝试过各种办法，做不出来。那么现在看来，这套办法呢是一个普实的。那么细节的呢，我并不，如果你感兴趣，你可以跟我联系，可以去看细节。但是观念上，这个问题实际上我们解这个问题，就是受益于咱们有限的矩阵的对角化里面的9-7方这样的一个想法，来把这个问题解出来的。那好，我的时间也差不多到了，那我的报告呢也就到此结束了。那谢谢大家。
好，感谢杨老师作为作者之一来给我们介绍这个 off diagonal 贝塔纳兹的重要方法。大家还有没有什么问题要问杨老师？目前好像暂时 大家可以下课之后再单独找杨老师问问题。如果暂时没有什么问题的话，那我们就再次感谢杨老师给我们2段精彩的报告。
谢谢大家。
多谢杨老师。
没什么。
那下面的安排就是我们稍微休息一下，有1个小时的时间，然后我们授课的几位老师在这儿的话，大家可以接着问一些问题。然后4点钟的时候，我们会有一个科普类的报告，是由现任的日本东京大学 IPMU 所长尤克亚马教授来给我们做。4点钟，但是应该是在对面的那个大报告厅。好，那我们暂时先休息1个小时。行。我现在可能有茶歇。
你是非常对他们女婿还是男？好像是，要么就是他儿媳是中国人，要么就是他女婿是中国人，在成都，所以他讲谈到成都去，我当时还不清楚，学做学术的，有可能是做学术的，有可能是做学术的，他是为什么？后来我看。
目前这边是结束了啊，这个
直播就结束了，
就是咱们 colloquium 就不直播的了。好，行，那就结束吧。
那个你说的，还有那个个人可以改为。不要看，应该一个简历吧。所以它的那个相空间习惯会。压力到多少？就在哪个标区间这一带，就是然后多少？那个是那个要最大的。我当时上来就是相当于看它这个光子呢，我光子快点
见过吗？